Hello everybody and welcome to today's lecture about short circuit calculations. Short circuit calculations belong to the wider area of network structure protection and operations. And now we look into the following grid. The grid is made up of a superlaying grid, two 110 kV parallel lines, two transformers in parallel, again two 20 kV lines, and a medium voltage network which passes on the current through a ring main unit transformer to the low voltage side. We want to calculate two types of fault locations. One is on the 20 kV level and the other one is on the 400 volt level. Let's start with the grid impedance. The grid impedance is given by the following formula. It is U squared divided by the short circuit level, and in this case we obtain a value of 0.10 ohms. So these 0.10 ohms are the result for the grid impedance on the 20 kV voltage level. The line impedances, as we can see here to our right side, are given by the specific line impedance multiplied by the length. And in this case it is 10.5 ohms for one line and half of that for two lines in parallel. So this is the real impedance for these 110 kV lines, but they must be transferred to the 20 kV side of the transformer, and that is done by the square of the voltage ratio. So on the 20 kV side, these 110 kV voltage lines have an apparent impedance of 0.17 ohms. Next is the transformer impedance. The transformer impedance is given by the percentage voltage times U squared divided by the apparent power of that transformer. And in this case we obtain for one transformer 2.4 ohms and two transformer in parallel is half of that. So this is the transformer impedance. The line impedance is calculated as before by applying the law of this specific impedance times the length, and we obtain 4 ohms for one line. We have two in parallel, so the lines altogether are 2 ohms. So now we can go to the synopsis and take the result. So synopsis means we add up all these impedances, which gives 3.47 ohms, and we have to divide the phase voltage for a three-phase fault by this value, and that comes out as a current value of 3.3 kiloohms. Now the question is, what is this current seen from the high voltage side, 110 kV? And that is given through the transformer by the inverse of the voltage ratio. And the outcome is 605 amps go from the superseding grid into this medium voltage grid fault. The next one is fault B, which is the fault on the low voltage side of this distribution transformer. So again, we calculate the impedance of that transformer, which is the product of the percentage impedance times U squared divided by the apparent power of that transformer, and the result is 30 ohms on 20 kV level. Now we add all these impedances up, obtain a total series impedance of 33.47 ohms, and divide the phase voltage by this value. The outcome is 605 amps on the 20 kV voltage side, which is our reference voltage level. Now the question is, what is the current on the low voltage side? So for the low voltage side we have to transfer this across the transformer by applying the voltage ratio, and here we obtain a value of 30 kiloamps. So the total result is given in this picture, 605 amps on the high voltage side of this ring main unit transformer, 30 kiloamps at the low voltage side. And that was the chapter about short circuit calculations. Thank you very much.